Hey guys, so this learning object is for the week of February 24th. The relevant textbook pages are pages 437 to 440. And it's going to be about sound intensity and power. So, what is sound intensity? Like, what are some everyday examples of it? I think it'll become more apparent to you what they are once I give a few examples. So, examples are every day you're exposed to different intensities of sound, and some examples are when you first wake up. So, when you first wake up, and you're the first one up before anyone in your house, and your room is silent, this is about 30 decibels. Don't worry, we'll define decibels in just a moment. Alright, and then 2. You wake up, you get ready, you go downstairs into your kitchen, and where now all your family is awake. They're walking around, they're out and about. This is about 50 decibels. Notice the increase. Alright, and then, so you go, you eat your breakfast, you do whatever, and then you have a little conversation with your mom before you leave for school. Your mom says, oh, have a nice day, and she's about 1 meter away from you. This is about 60 decibels. And then, so you leave home and you wait for the bus at Cambie and Broadway. You're waiting for the 99 to go to UBC. This is a busy road. There's a lot of cars going by, there's a lot of people, and this is about 80 decibels. Notice the increase as we keep going down. And then, so finally you get to UBC and there's construction everywhere. You're about 1 meter away from the construction site and it's super loud. And this is about anywhere from like typically 100 to about 110 decibels. So notice that as things get louder, the decibel levels do too. Alright. So, what is sound intensity really? Like in a physics sense. Sound intensity is defined as, so I for intensity, and defined as, the 3 lines always means defined as. It's defined as the energy of the sound wave going through an area. This is usually like air if you're speaking out loud or if you're playing music. And this is all divided by the area, we'll write that out, times the time. So we know from past physics courses that power, or P, is equal to energy over time. So we can define I, therefore, 3 dots means therefore, as I is defined by P over A. Now you might be wondering, what is A? A is the area. But you need to consider that when you make a noise, does the sound go out in a flat circle, like a ripple in a water, 2-dimensional and it's flat and it's a circle? The actual answer is no. Sound propagates isotropically, which is a very fancy word that just means in a sphere. So it's actually 3-dimensional, which is most things in life. Therefore, we define the area as a surface area of a sphere, which is equal to 4 pi r squared. So intensity also has a huge range. Its range for humans are basically, let's say range. The faintest noise a human can hear is 10 to the negative 12 watts per meter squared. And you might wonder, where did this unit come from? And this unit comes directly from what we just defined intensity as. So as intensity is defined as the area going through an area, the energy going through an area, divided by the area times time, or rather, power divided by area. We know that power has the units energy over time, which is equal to watts, and area is always in the standard unit of meters squared. So in the end, we get I is in watts per meter squared. And I'll just circle that in a different color for you. So we get the range for the faintest noise is 10 to the negative 12 watts per meter. faintest. And the loudest we can hear before your ears start to hurt, or right when they start hurting, is... This sometimes causes your ears to bleed as well. It's actually 1 watts per meter squared. As you can see, this range is huge. It's about 10 to the 12 watts per meter squared. And the way I got that was to divide 1 by 10 to the negative 12, like the loudest to the faintest, and that's your range. So, as physicists and mathematicians and scientists, we get lazy. We don't want to keep writing this huge number down. So they actually came up with this way to make the intensity sound level range easier. And it's called a decibel system. So a decibel is defined as dB, which equals decibel, and deci means 10. Okay? And the symbol for decibel is this sign right here. And the decibel level of different intensities, I for intensity, equals intensity level rather than the intensity itself. So the key word here is level. Decibel is always in relation to another intensity. In relation to another I. And this means that it's in reference to something else. So you need a reference point for you to calculate the decibel level. As a decibel level is basically the difference between 2 different intensities. So we actually define decibel level of an intensity as 10 log base 10 divided log of intensity, either the intensity given or the intensity you're trying to figure out if you have the decibel level, divided by, here your reference will always tend to be your intensity naught. And here, as we know, I naught is equal to the faintest noise humans can hear, so 10 to the negative 12 watts per meter squared. As you can see here, we always want a unitless expression inside of your logarithm. Therefore, you have your I naught is 10 to the negative 12 watts per meter squared. Therefore, when you divide an intensity by your I naught, you will cancel out the units as well. The reason it's called decibel, I'm guessing it's because there is a 10 here, so that can be an easy way for you to remember, as deci equals 10. We went over this. So, to review, we went over what I equals, and I is intensity, and I is defined as power over area, units equals watts per meter squared. We also defined watts per meter squared, which is also equal to P over 4 pi r squared, which is surface area of a sphere, as sound propagates in a spherical manner. A better word would be isotropical, as you can look that up in your textbook. I'll write it down for you. And therefore, we also defined the relative level of intensity, so relative level of intensity decibel system as B on the intensity 10 to the log of, and whenever you write log, you always assume it's to the base power 10, I over I naught, which is always going to be 10 to the negative 12 watts per meter squared. And therefore, if someone asks you in decibels what you want, you would always use this equation. You'd solve for B if you know both I's, and you know 10, and you know log, and it becomes pretty simple. So what are some examples? I'll give you a warm-up one. Example 1 is, if you measure sound intensity to be 363 times greater than that of the reference sound intensity, I naught, what is the sound level in decibels? So I'll give you a minute or two to figure that out. The options are 15.6 decibels, 1.56 decibels, 25.6 decibels, and 2.56 decibels. So to figure this out, you actually would do the following. You would start by noticing that your I naught is your reference. So RP means reference point. And it's equal to 10 to the negative 12 decibels. Alright, so that's the easy part. Your I here is equal to 363 times greater than your I naught. So it's equal to 363 times I naught, which is equal to 363 times 10 to the negative 12. Oops, sorry, here it's not dB. What am I doing? It's watts per meter squared. Watts per meter squared. Alright, and you know your equation for decibels is this sign over here equals 10 log I over I naught, which is equal to 10 log 363 times 10 to the negative 12, 10 to the negative 12. And here you always have watts per meter squared. Sorry if it's a little messy. Watts per meter squared. As you can see, it's not very important because it always cancels out. So here it cancels, here it cancels. As well, you can see that your 10 to the negative 12 cancels. So you're left with 10 log 363. This actually ends up being about, if I put it in my calculator correctly, it is 25.6 decibels. Don't forget your units. So, second example is to understand the decibel levels. So if a sound is 12 times as intense as another, what is this difference in decibel levels? And in this example, you can see that decibels are a way to measure the difference between two intensities as we're taking the difference. So the different options are 12 decibels greater, 12 decibels lower, 4.77 decibels higher, or none of the above. So your answer will actually be D, none of the above. We know that the ratio of the two intensities, so the ratio I2, the second one, divided by I1, equals 12. Here then you take the difference of decibel levels, because that's what you want. You want the difference in decibel levels, right? The difference in decibel levels. So you don't want the decibel level of intensity 1 or of intensity 2, you want the difference between them. So you would take the decibel level, the delta always means a difference, which is B2 minus B1. Therefore, your your decibel level is always equal to 10 log I over I naught. And here you have your delta equals 10 log I2 over I naught minus 10 log I1 over I naught. And remember that when you have log, you have log A minus log B equals log A over B. This is key to remember. So therefore you have the difference is 10 log, and this one is going to be a big one, so it's going to be I2 divided by I0 all over I1 over I0. Here you can see that your I naughts cancel out, and you're actually just left with 10 log I2 over I1. From here on out, it's just plug and chug. So to save some paper, I'll just flip that over. Hope it's not too hard to see. Then, so as this was, your delta was equal to 10 log I2 over I1, and you plug and chug, it's equal to 10 log 12. And this is because you know the ratio of both your intensities was 12. And from here on out, it's just go and put it into your calculator. And my value is, let's do this together. 10, so log 12 equals, so it's about 10.79 decibels. And last but not least, this one is the most interesting example in my opinion. I'm going to do a real life example. So what is I'm going to ask two questions. A, the intensity, and B, the power of my voice. So I actually downloaded this cool app, and it's called the Decibel Volume, and it actually measures the decibel of the noise. So I'm just speaking in normal conversation, and we'll just take the range. It's going to be approximately, I'll say 62 decibels. So here, I'll just write that down, equals 62 dB. So calculate the intensity and the power. And try to figure out, does this correspond to our introduced value of a normal conversation? And if you remember, that was, I believe, 60 when you talk to your mom. Does it respond, is it around that? Alright, so as we measured it to be 62 decibels, therefore, my intensity will be, to know which equation to use, you always just have to look at the equations you're given. So you have intensity as power over A, or the power over pi for r squared, or you have the relative level of intensity, the decibel system, which is equal to 10 log intensity over intensity naught, and you would practically choose this one because you're given the decibel level, which is 62 in this case, and you're also, you know, intensity naught, you know I naught, it's always going to be 10 to the negative 12 watts per meter squared. Therefore, so for your intensity, you would use naught equals 10 log I over I-O. Here you need some basic math. Everyone should basically be at this point in their math level, but if not, I'll just go over it. A rule with logs is that log A, B equals C, right? This is also equal to C, A, C equals B. So to solve for I, we actually need to take away the log. But first, we'll divide B by 10, which equals log I over I naught. And we know B was approximately 62 decibels equals log I over I naught. And here we know log is a base 10, so your A value here is actually going to be 10. Like, you can always add a little 10 to just remind yourself, but so therefore, by using the log rule, you can get 10 to the power of C, C here is 62 divided by 10 decibels, equals to the inside of your log, so I over I-O. And then you need to isolate for I to get the value, so you end up getting 10 dB times 10 to the negative 12 watts per meter squared. This, sorry for all the arrows, but is equal to, I'll just write equals to I equals to, let's do it together. So 62 divided by 10, you can always input 6.2. And then my calculator for 10 to the negative 12, you always have to enter 1e negative 12, probably do for yours too, which is equal to 1.58 times 10 to the negative, I count 6 decimal places, so 6 watts per meter squared, and that is your answer. So the second part of the question is asking, what is the power? And here I assume that I'm about 0.5 meters away from the phone. I'm just sitting down and slouching at it. So the power is equal to, as we know from our review, that I is equal to power over A, or power over 4 pi r squared, which is the surface area of a sphere, which is the way sound wave propagates. So I is equal to pi over A, and you can always rearrange this to make it so power is equal to I times A. So your power is equal to simply what we calculated in our last value, to be 1.58 times 10 to the 6 watts per meter squared. And it's always important to write your units. Just don't forget that. It'll become way easier for you in a test or an exam for you to figure out if you have the right answer. So this is your intensity times your area, which is 4 pi r squared. And your r here is going to be how far you are from the sound source. R equals distance from sound source. Alright, so when you just plug in check, and I still have my value for intensity in my calculator, so I'm just going to keep that and times it by 4, times it by pi, times it by 0.5 squared. And I get 4.979 times 10 to the negative 6. And you know that it's watts because meter squared cancels out. Sorry, I'm talking about units. I forgot to put my own. So that's meter squared. Meter squared equals watts.